Okay, at the end of class today, we were talking about what happens if the force is not constant. What happens if it's changing? So the equation W equals F delta D cos theta. This equation will work whether the force is constant or changing. But to solve the problem mathematically, that has a changing force requires calculus. So we could find the average force or we could use calculus. But we can solve this problem graphically if it has a changing force. And what I mean by that is you do a graph and you put force on this side, measured in newtons, and this would be displacement, measured in meters. And so if the force was constant, it might look like this. But if it's changing, whoops, imagine that went down straight, it might look like this. Okay, and so let's see, 1, 2, 3, 4, 5, 6, that'd be 7. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So what you do is find the area underneath the curve. So you would bring this down. I don't know which one I was going for. 1, 2, 3, 4, 5, 6. So I guess it's going to be 6.5. And so you would find the area under this. And so the area is just base times the height. So it would be 7 newtons times 1, 2, 3, 4, 5, 6.5 meters. 72, 75.5. So A would be, I said 70, but I meant 40. 45.5 meters times newtons times meters joules. And then we would do this part, and this part is also 6.5, so the area of a rectangle, half the base times the height. So 1/2, 7 newtons times 6.5 meters. So 1/2 of 45.5 will be 22.75 joules. And so the total area would be these two added together. So it would be 66, 67, 68.25. I could check that just to make sure, I suppose. 7 times 6.5 plus 7 times. So yeah, 68.5 joules would be the total area, which would be then the total work done. If the line had continued down here into like a negative section, then you would find this area, and it would be negative, I don't know, maybe to be something like negative 20 joules, and so then to get the total, you would add negative 20 to this, and you would get 48.25, okay? So if it's under the line, the x-axis, then it does go in as negative work done, okay? So one question for homework was page 229, number 11. And it is finding the area for examples where the work is being done by a force that's changing in size. Okay, so that was one of the pieces we didn't get to today. And the second piece we didn't get to today, that will take just a couple of minutes as well, is looking at power. So we've looked at force, now we need to look at power. So think about two of us, you and I, pushing a box down the hallway. I have a box, you have a box. The two boxes are the same size. We're starting at my room and we're ending up down at the next classroom. So the work we're doing, the force we're using to push it, the distance we're pushing it over, the work done is the same. But what might not be the same is the power, because power is equal to the work done in a given period of time. It is definitely possible that you might get your box to the other end of the hallway before me. Your time period could be less. And so if power is equal to work over time, if your time period is less, then your power is greater. Symbol for power is capital P, And so P is equal to W over delta T, where the W is measured in joules, and the work is measured in joules, and the time is measured in seconds. So power is measured in joules per second, which we rename. What is the unit of power? You know this one. It's what's written on your light bulbs at home. It's a watt. W-A-T-T. Its symbol is a capital W. So if you did 100 joules of work in 10 seconds, then the power you've developed is 10 watts. If you think about like going to the gym and doing a workout, the first time you do it, it might take you like a half hour. But by the end of the second week, you might have it down to 20 minutes. The amount of work you're doing is the same, but the time period is less, and it means you're getting more powerful. Or maybe it's you shoveling your driveway since it's snow season. First time you shovel it, it might take like an hour. By the end of the season, after a lot of practice, you might have it down to like 40 minutes because you have become more powerful. The amount of work you're doing is exactly the same. It's just the time period no longer needs to be as long. Now there is a second equation for power that you do not often see, but let me just show you so I don't deprive you of anything. Knowing that work is equal to F delta D, we put that over delta T. We know that delta D over delta T is actually a VAV. So you may now and again, occasionally, see an equation for power, which is VAV times delta, F times VAV. But the work over time is the most common one, okay? And so your other 3 questions for homework tonight is with this equation. Oh, one other thing, the old unit of power in the empirical system, in the system that used pounds and miles and inches and all that stuff, the unit for power was a horsepower, defined by the power of the king's horse. And 1 horsepower is equal to 746 watts. And I'm telling you this because in one of your homework questions tonight, it asks you to convert it into horsepower. So you'll find the answer in watts, and then you'll divide it by 746 to figure out how many horsepower that is. Okay? And so the other questions that I had asked you to do were on page, I think it was 266. Yeah, 266, numbers 41 to 43. Okay? And so go test these guys out. They shouldn't be too bad. And then I will post the solutions.